Okay, so good afternoon, everyone. The topic for today's class is light. We'll be going through the ray diagrams and numericals of this chapter. So first of all, can anyone tell me what reflection is? Just a small definition. We have learned about reflection in the past. Also, we have learned about it this year. So can anyone give the definition or some idea about reflection, the whole term?
Reflection of light is the phenomenon of bouncing back of light in the same medium on striking the surface of any object.
Okay, yeah, that's the exact definition. So, reflection of light is the phenomenon of bouncing back of light in the same medium on striking the surface of any object. So, as you can see in the figure here, the bouncing back of light, it happens in one medium, unlike refraction. Reflection, it takes place only in one what do you say, medium. And over here, you should be noticing that the angle through which they bounce back is also same. If we consider this as this is the incident ray, you have to check the arrows. So so this is the idea of reflection. It's not our topic right now, but then we'll just have a small idea about it. Now, the laws of reflection of light. So one second. Okay. So the laws of reflection of light, there's two of them. We have a good idea about this because we've learned this in the past as well. So first of all, the angle of incidence is equal to the angle of reflection. It's, you can see it from here. The angle of incidence will always be equal to the angle of reflection when light bounces back in the same surface when reflection takes place. Okay. Now second one is the incident normal to the mirror and the point of incidence and the reflected ray all lie in the same plane. So over here you can see the incident ray, this ray over here, this light is touching the surface at this point. The normal is touching the surface at this point, and even the reflected ray, it's going away from this point. So they all they basically all these 3 points, that is the incident ray, the normal to the mirror at the point of incidence, and the reflected ray, they're all lying in the same plane. You can see it because all of them are like on the same plane over here. It's this one. So this is just to give a small idea if we have forgotten the first chapter. Okay, so now we're going to start off with some basic rules that you should know to draw a ray diagram. So one second. Yes, so picture got cut a bit. Okay, one second. Yeah, so basically the intersection of two rays, reflected rays, can give the image of a point object. So you can get the image. So suppose if I have an object over here and this is the mirror. Okay, so basically this is to be a bit more bigger. So if you want the image of this object in a concave mirror, this concave mirror, you should get the intersection point of two rays. We've learned about this, right? So it can be like, it's not that good right now, but then so this intersection point over here, this is where the image will form. We'll do it better, like in a better way, but just to give an idea. So wherever two like reflected rays meet, that is where the image of the point object is. And you can consider any of the four following like rays. So there are four different ways where you can, through which you can draw, like, what do you say, um lines of a ray diagram. So we'll be going through all four of them. Okay, so Kadir, you can take over now. Kadir.
Yeah, okay.
Yeah.
Um, the did you explain them the intersection of at least two reflected rays?
Start from here. I did it here.
Okay. Array parallel to the principal axis, which is after reflection, will pass through the principal focus. Principal focus is the F, the point over here. 1 minute, I'll just get the. Can you see my mouse? Can you guys see my mouse?
Yeah.
Okay. So the F, this point is the focus. This is the principal axis. Over here, this is the angle of incidence and the angle of reflection.
No, so over here, basically, this is a basic ray diagram. Okay, so this picture got
Yeah,
cut a bit.
this
So
has
like, don't
no
consider
rule
this.
or
Okay,
something. This just
got cut a bit.
yeah.
Let me just take this.
Okay, a ray parallel to the principal axis after reflection will pass through the principal focus in case of a concave mirror, or appear to diverge from the principal focus in case of a convex mirror. That's it. 1 minute. Yeah. So in case of a concave mirror, this ray of light it will go through the principal focus, and in case of convex mirror, it will diverge.
So you can check these two ray diagrams as well. This is the first one for
This
concave and second one for convex. You can see over here, this is parallel. This ray of light is parallel to the principal axis. So this is the principal axis. Okay, from this recall it. This is the principal
the
axis.
point P. This point P.
This straight line is the principal axis. So this is pole. Okay. Now this line is parallel. The what do you say? This line is parallel to the incident. I mean the principal axis. So it will pass through the focus. This is the focus, by the way. And for in the other case for convex mirror, it appears to diverge from the focus, so it does not actually touch the focus, it just appears to diverge from it. So that's the first point. I will be going to the second point.
What happened?
Nothing. Okay, let me just clear the screen.
I'll clear it.
Okay, so next one. So the second one is a ray passing through the principal focus of a concave mirror, or a ray which is directed towards the principal focus of a convex mirror after reflection will emerge parallel to the principal axis. So you can see over here is that this is the what do you say, incident ray. So it starts from a like it passes through this focus point and it touches the mirror surface. Now since it passes through the focus, it should appear like what do you say, reflect parallel to the principal axis. So that is the rule for concave. Now for convex, you can see that a ray of light that is striking the mirror, convex mirror, and it is direct when it is directed towards the focus, it will emerge parallel to the principal axis. Over here you can see it. So just keep this in mind. It will be useful when we are doing the not numericals, basically the ray diagrams. So yeah, the third rule now.
And in the concave and convex mirror, in concave mirror, the what do you call, the ray of light will always bounce back. Like it won't, you won't see the image par the other side. But in convex mirror, the image will be found on the other side of the object. Like in this case, this is why the line over here are dotted. Okay, a ray passing through the center of a curvature of a concave mirror, or directed in the direction of the center of curvature of a convex mirror. After reflection is also reflected back along the same path. So in the third case, in both the concave and convex mirror, when the ray of light in first in concave mirror, which is this one, when the ray of light passes through the center of curvature, it touches a mirror and it bounces back in the same path. Even in this case, when the ray of light is passing through the center of curvature, oh yeah, you can see the ray is coming from here, this position, and then it bounces back over here. But just to show that this ray of light is passing through the center of curvature, we show this dotted lines.
Okay.
Done. I'm on next.
The next one, the last one is so this one like you can try your best to use the first four rules, but then you can try this as well. This is the last one is a ray incident obliquely to the principal axis towards a point P of the pole of the mirror on a concave mirror or a convex mirror. For both of them, it is reflected obliquely. The incident and reflected rays follow the law of reflection at the point of incidence P, making equal angles with the principal axis. So basically, you can see what do you say, a ray of light that comes toward and strikes towards the pole of the mirror, and when it strikes the pole, it's reflected obliquely, that it's basically diagonally. And what another thing about this is that it always follows the law of reflection. So to
And
give
I'll
a
move this ad.
idea, yeah,
This ad.
yeah,
There's an ad on your screen, I guess.
oh yeah, 1 second, yeah. So basically,
Went.
if this is a mirror, a convex mirror, okay, a concave mirror. Okay, so if this is a concave
If
mirror,
a ray of light passes, yes, it is.
and this is the object, so the ray of light, it it touches the principal axis. Now suppose if this is 30-degree, this is the pole, okay, so when it touches the pole at a degree of 30-degree, it will also get reflected at an angle of 30-degree. So that's basically it. So that's another rule. So these are the four rules you have right now. You can use either one, two of them. So because we need two rays for the things to, like, what do you say, we need two rays to get an intersection, right? So what we need is an
Get two rays
intersection
because
point.
one is angle, the incident ray, the other is reflective ray.
Yeah, so suppose if this is the intersection point, we need at least two rays to find the image of an object. So it's just to give an idea. So now we'll go on to the ray diagrams. So first of all, we're starting with the concave mirror. So Kadir, you can try. So
Okay,
first of all, do you all want us to show it, or like as in draw it and show, or else you just want us to explain the figure? You want to like you want
I
it to be
think if we
drawn?
explain it like this, it will be easy because drawing, I don't think we'll be able to
Just
draw
explain,
properly.
drawing is small.
Okay, fine.
Fine,
If
we'll
you
explain.
look, if you want, I'll try one. You can just check it out if you want. Okay, one second, 1 second. I'll try. Okay. Okay, fine. So this is the mirror. Okay, just 1 second. I'll just make it a bit more straight. 1 second.
I mean, I'll draw. You disabled my thing.
Okay, so this is the principal axis, okay? And this is the 1 second, 1 second. If I give them, you can control my screen. I'll give you that 1 second.
Okay, fine.
So if this is the concave mirror, okay, so this is the mirror. So we'll mark all the stuff in the beginning. This is the pole, this is our focus, and this is our center of curvature. 1 second. Yeah, this is our center of curvature. So the distance between CF and FP should always be same. Just keep that in mind. Now our first one is, you can see the PPT now, right? Yeah.
Yeah, we can see.
Okay. So the first one is if the object is at infinity. Okay. So let's try it out. So we have our object at infinity. So let this be the object. Okay. So now so this is the object. So the first ray will draw it parallel to the principal axis. Okay. One second. Let's take another one. Okay, so let's draw it parallel to the principal axis. So it intersects over here. So when a ray is parallel to the principal axis, where does it pass? Can anyone tell? Fabio, can you tell? It's parallel to the principal axis. So where does it pass?
It passes right through the focus.
Passes through the focus.
That's correct.
So it would go like this, right?
Focus is also called sometimes principal focus. So it may confuse.
So next, if a ray of light passes through the focus, where does it reach?
It will be parallel to principal axis.
Parallel to the principal axis. Okay, so this works, right? You can all see it, right?
Yeah.
Okay, so okay, so basically, if when you have an object at infinity, and then the all ray of light, you can draw as many rays of light as you want. It will all go parallel to the principal axis, and it will reflect and it will converge at the focus. So it is a point-sized object because you can literally see there's no image formed. Usually, we can see an image like this, or in concave mirrors it's inverted, so it will usually be like this. But over here it's point size. It's literally point size. So it's really small, and also it is real and inverted. So real means it can be obtained on a screen. So yeah, that's the first one. So now we can go for the second. Next one.
But I'm unable to write or draw something.
Okay, so yeah, try.
Not coming.
Okay, I'll do the ray diagram then. I'll try that. Okay, so the second one. Oh, 1 second. Khadir try.
Wait, I'm trying. Keyboard layout.
Oh god.
Okay, yeah, it's coming. It's working now. It's working.
You can just do backwards.
Fine. Okay, I'm drawing now. Let's see. Wait, Aman, I'm controlling your screen. It's not like
Sure.
how I did before.
Okay, let's just try it out. Okay, I'll just quickly do it then.
You only do it. It's fine.
Okay, so the first one is, the second one is when the object is beyond C, the image is formed between C and F. So let's see how that works. So over here, let's draw the mirror first. So this is our mirror. Okay, wait, it's not the shape.
Beyond C means when the object is at infinity, when you can't see the object in this ray diagram. You draw the object outside the line or very far away from C.
So over here we have our pole over here. This is our focus, and this is our center of curvature. Okay, so when the object is beyond C, right? So let's draw the object over here. Okay, one second. Let me just take an arrow. Okay, so this is our object. Okay, so this is our object
And
beyond.
people usually get confused with beyond C and at infinity. So
Huh?
just tell them that. People usually
This
get
is
confused.
infinity. Infinity is always outside the. Okay, that's not the way.
This is
Infinity is always
infinity.
outside the principal axis. Like you should show outside the principal axis. Wait, I'll show
This
the.
is infinity and this is beyond
Okay, I'll
C.
show infinity once more.
They both are different.
Okay, I'll show infinity once more. So this is infinity. So first ray is parallel to the principal axis. It will pass through the focus. Second ray passes through the focus and it will go parallel to the principal axis. So you can see that the intersection point is at the focus. So that is the first one. So the image is point sized and inverted. So we did this. Now for the second one, let me just clear the screen. Where is it? The second one is when the object is beyond C. So let's just draw the, okay, there's no line over here. Okay, so this is the ray, I mean the principal axis. Now let's draw the mirror. Okay, so this is the mirror. And just make sure that you're drawing the silvering. So this is the silvering. Okay, so this is the reason why the light gets reflected. So the silvering has to be there. And in the case of a convex mirror, the silver would be inside. Okay, just keep that in mind. It would be opposite to the reflecting surface, because in convex mirrors, the reflecting surface is the back of the mirror, and over here it's the open side. So the silvering is backwards. Okay, so let's just name the stuff now. Okay, so this is pole, let this be F, and the force for focus, and let this be the center of curvature. So now okay, so let the object be over here. So you can clearly see that, okay, one sec, the other way around. So you can clearly see that the object is beyond C, because C is over here and the object is beyond it. So now the first is same thing. You have to do the same thing, parallel to the principal axis, and it passes through the focus. This time it passes through the focus and it's parallel to the principal axis. So the object is formed over here. That's it. Is there any doubt? So basically the object is formed in between C and F, that is center of curvature and focus. It is diminished, it is small, because the object is, you can observe the picture and see that the
And
object
it's inverted as well.
Yeah, the object is big, but then its image is small, and also it is inverted. Inverted images means the ones that come below the principal axis. It's also real because
So this is concave, right?
concave, yeah.
Yeah. So in concave mirror, mostly all the images are inverted, right?
Except one, yeah. Except one type.
Yeah.
We'll go through that. Now the next one. Is there doubt in this? Any doubt? Same thing. We'll be doing literally the same thing.
No, it's fine. Next.
Okay, next. So the next one. One second. Let me just clear the screen. Not getting cleared. What the heck? One second. Yeah, next one. So this is, oh no. So this is the principal axis. Yeah, principal axis. Same process. This is the mirror. And you can, yeah, just make sure that the mirror, it's silvered properly. Okay, I'm just roughly drawing it for now because it's not that easy right now. So next one is when the object is placed at C. Let's see what happens. So the silvering is there. Now let's name the places. This is P. This point over here is P. This is F. Let's take this as F, and let's take this as the center of curvature. So now the object is placed at C. Okay, so basically it would be like this. So this is the object. Now same thing, we'll be using the same rule because this is the most convenient one, because like we don't have to measure the angles and stuff like the fourth rule. So the first ray goes parallel to the principal axis and passes through the focus, and the second one is passing through the focus and it goes parallel to the principal axis. So it should be coming right over here. If it should be like this ray diagram, it should be perfect, or it won't pass through it. You can see over here, this is a small deviation. Like it should be a bit more towards the right. So when you draw it, just make sure that your measurements are right. Like the lines should be absolutely parallel. So you have to make sure that you start like right at the tip of the object. It has to pass exactly through the focus. Only then you will get like both the object and its image on the straight line. And it has to be, you can see over here, like both of them should lie on the straight line, because that's how it is. It will be of the same size, and the object is real and inverted. Real means you can see that it's on the left side of the mirror, like in the on the reflecting side basically, and also it is inverted. It's below the principal axis. Now next one is when it's placed between C and F. Okay, between C and F, right? So it's over here. So enough, same thing. We literally the same thing. We're just doing the okay. So okay, our image is formed, and where is it formed? Can anyone tell? I'm gonna point it, but Fabio, can you tell where the image is
It's
formed?
on beyond C.
Beyond C. That's what exactly right. So it's just beyond C. So you can see that the whole pattern is reversing now. It's going backwards. It's becoming bigger and bigger. You can see that the image is now enlarged. So this is the first case of concave mirrors where the image is getting enlarged, and also it continues to be inverted. It's beyond C, and it is real. So it's literally the same thing, but just make sure that you have the arrows as well, because okay, that's not that kind of arrows, but then this kind of arrows. So you have to point towards where the ray is going, or else no one will understand how your rays are going, because it can come from here as well, right? It can go like this. You won't know. If you're not writing this, then you won't know where the ray is going. You can write like this, right? But it should be shown that your ray goes from here and it goes parallel here. So everything will be understood, or else you'll have to write about it. So we'll just demonstrate the whole process through the ray diagram itself. So yeah, that's the next one. So now the second last one of concave mirrors. Okay, so this is where the object is placed at the focus. Okay, that's not the second one. Second. So here the object is placed at the focus. So this is the object. Okay. Now, according to the rules, the same rule we'll be using, parallel to the principal axis, passes through the focus. But for this one, can you draw it? Like, can you draw a ray that passes through the focus? Anyone
No,
can?
we can't.
It's on the focus. Can you draw? So what do we do?
The image is found at infinity, right?
Image formed at infinity. Okay, so I'll just tell. Now this is your point. This is your. Just take this point and one second. Not the correct point. Okay, 1 second. So you need a scale for this, or else it's going to be quite tough because it has to pass through the principal axis. So let's just take this like this. Okay. So you're seeing that this is the third diagram. What do you say? Third rule. If a ray of light passes through the center of curvature, it goes without any deviation. You can see that it. First of all, the ray starts from the object, it goes towards the mirror, and it gets reflected back because it's incident. It's like incident on the mirror, and it passes through the center of curvature. So suppose, so you get the rule right. Is there any doubt in this? That's the rule, right? Okay, so this was the rule. So a ray of passing through the center of curvature of a concave mirror is reflected back along the same direction. And over here, you can see that I'll use the pen. So passing through the center of curvature to the mirror, and it's reflected back along the same direction. It's passing over here. Okay, now
The image is formed at infinity.
yeah, so you just show the dotting. It will never meet. It's not possible. Like it might meet. Like that's how
At
we
some
assume
point,
it.
it might meet, but
You
it's not
know that
possible.
infinite, like the lines that are parallel to each other, they will meet, but then it's at infinity basically. That's how we consider it. So they'll meet an infinity, but then we can't show infinity obviously. So you can just leave it like that. But just make sure that you're drawing your arrows and stuff. It has to be shown where it's going, and that's it. Nothing else. So yeah. Now we go to the special case. So till now, wherever, like even this one, even in the infinity case, the image formed is real, inverted, and it's highly enlarged because it's formed at infinity. But this is the last case where the object is formed, where the image is formed on the other side of the mirrors. Now this is because, so what do you call images that are formed on this side of the mirror, like behind the mirror? Anyone remember? Still now we did real images, like we got all of them as real
Yeah,
images.
this is
What is it called?
can someone tell Ayan?
Ayan. Anyone? Open.
Badiruddin, Ayan, Fabio, Ritvik.
Called?
Is it virtual?
Yes, it's
Yeah,
virtual.
virtual, correct.
Virtual image. So here the image is placed right in between the okay. You can place it anywhere in between. Okay, so you don't need to place it exactly between. You can place it anywhere between the pole and focus. So there's two ways of doing it. First one.
Should not. It should be after pole and before the focus. Sorry, after focus and before pole.
Okay, so this is the first rule. The first, we are using the same rule.
Parallel, first ray is parallel to the principal axis and it goes through the focus. Second ray goes through the focus and it comes back on the same way.
But you can draw it, trace it backwards. Okay, just trace it back,
because in this case the image we can't see any image forming.
Okay,
so we just take it over there.
You're supposed to, there's a method like this. We are supposed to do it like this. Okay, but then for simplicity, let's take the other one. Let's take the one where it goes like this. Okay, you can see my figure, right? First of all, we told like two rays should obviously meet. That's how we do it in physics. Okay, now in the infinity case, we did not tell that it doesn't meet. We told that it meets at infinity, right? And why does it meet at infinity? Okay, so I'll just tell, I told it before because both the rays were parallel, right? And we know that parallel lines always meet. It's kind of related to maths as well because parallel lines always meet, but it meets at infinity. So we obviously can't show that in our ray diagram. But is this parallel line? Are these parallel? Like, can you
No,
see?
they're not parallel. How are they parallel?
They're not parallel, right? Parallel means it should be, if this was parallel, then it would be something like this, but it's clearly diverging. Like they both are moving away from each other.
Diverging. They both will never meet.
Yeah, they'll never meet. So it's not possible. Like you can't get it to intersect. So you trace this also backwards. Just trace it backwards and just hope that it meets. And you can see that it meets at one point. So this is the.
In this case, the image is enlarged, erect, and virtual.
Yes.
Erect means upright, like a normal.
Any doubt? So you can see it's clearly like this is the image object, and you see how big it is. It's really big, much bigger than the object. Also, it is erect. It's virtual. You can obtain it on a screen. All the stuff.
Aman, just go to the periodic slide for a minute.
Yeah. This is convex.
But in this case, the image is small over here, right?
That's convex. That's convex. This is the one.
Oh yeah, this one, yeah.
So yeah, that's the last one. So that's concave mirrors. Now let's go for convex.
That's convex. Come on.
1 second. I'll have to draw.
I don't think for convex we need to draw. They understood, I guess. We can just draw over there.
What?
For this convex mirrors.
Yeah.
I don't think we need to draw. It's simple.
Yeah, I know. Just anyway. What's the point of this? Nothing. It's not that big anyway. The whole topic. So let's just do it.
Okay, I'll do it.
Yeah, you can try. You can do it with the zoom feature. 1 sec. I'll just try the zoom feature. Annotate. You can't. If you take control of my screen, you can't do it. Take the
I'm
other.
getting an option for annotate.
No, you're using remote control option. Remote control means you're controlling my screen. Take the other one.
Okay, so you remove it from the remote control.
Yeah, you know.
There's no annotate option for me.
You did it in the beginning.
Yeah, I don't know what happened. No, it's not coming. Just enable it.
Try.
It's still not there.
Just close the thing and check. Once more.
Right, now keep.
Okay, fine. Try.
Okay.
I do it for you. 1 second. That's F and that is C. Okay, 1 second. Okay. I'll just erase this thing. Okay, you can do. Yeah, you can try. So the first one is object is at infinity, so it has to be outside the principal axis. So you can start now. Yeah, Kadir.
Wait, I'm gonna, you just do the first one. I'm getting some problem. I'll do the second one.
Okay, fine then. So, okay, first of all, concave everyone is fine, right? Is there any doubt? You don't need to by heart anything. It's literally logic. You can see, like, just check all the ray diagrams. You're using the same rule, okay? Apart from this, no, this is also easy. Just pass the, like, you can understand it when you see the image itself. Like, you know that it will never pass. Like, I'm talking about the one that passes through the focus. That rule, okay? So when you're placing the object at the focus, obviously you can't pass a ray through it. So that's why you're taking C. But apart from this, you literally see that all the rules are same. Like, we're using the same rule. Passes through the principal axis, the first one, and the other one is parallel to principal axis, and it passes through the focus.
Okay, Aman, let's do convex mirror. I can now do it.
Okay, fine. I'll get to the slide. So it's all the same rules. Okay, we're using the same what do
You
you
just
say,
have to
rule,
use just
but
a
it
bit
passes
of
through the focus.
sense.
So does anyone have a doubt here?
Ayan, Fabio, Ibrahim. Ibrahim is it?
Till here. This is a special case.
Badruddin.
Just keep this in mind. It's a bit more important than the others.
Okay, fine.
Okay, fine.
I'll do. Okay. Get to the slide here. In this case, the image, just increase it like this.
No,
The
you,
image
you
is
don't need to draw that. It's not there.
fine. Just
Principal axis is already here. This is the principal axis. Only this.
yeah. So image is formed here at infinity. 1 minute. I'll just make it proper.
Okay.
Wait.
Yeah, object is here.
Yeah, object is here, I think.
Yeah. Take this.
Fine, you see. Okay, object is here. So you see the first ray. What happened? I'll do it. Leave it.
Yeah.
Fine. Okay, so you see the first ray. It goes to the top. It hits the mirror, and it reflects. What happened? Yeah, and it reflects the outside. So it's diverging, and this ray will never meet any other ray. And the second ray, it goes to the middle, goes here, and comes back. Same way it comes back here. So in this, these both rays don't meet. And the third ray goes from the bottom. I'm doing no need.
It should be touching the pole, okay? Just keep that in mind.
From the bottom, and it again diverges outside. So all these three rays cannot meet, but we have to form an image. So what you got to do is you have to just pull this back towards the focus, like this, and this ray over here, you pull this back over here. So we can see that these two rays are meeting at the focus, and the image will be diminished, but it will be virtual. The image will be diminished, virtual and erect, right?
A small thing, I think, just kind of a suggestion, okay? 1 second, I'll just clear the screen. I'll show that once more. It's the same thing, okay? Now the first ray is touching. One second, shit, that's the wrong one. 1 second, sorry, the wrong one. Okay, so in this one, the first ray is parallel to the principal axis. Just imaginary principal axis over here. It's parallel to it, okay? Now you don't directly draw the reflected ray. You trace it from the focus. It should go like this. That's how it should go, because it should pass through the focus. And you make it dotted, just to show that it's not actually intersecting. So yeah, even the second ray, okay, yeah, second one is correct. You should touch the principal axis. Okay, just touch the principal axis and it will go back. That is the second one. Okay, that's not the one. Yeah, goes like this. Yeah, something like that. The third one is same thing, parallel to principal axis. Now it touches the focus. Okay. Oh my god, what happened? Yeah, it touches the focus. What is happening?
I don't know. Wait, okay, I'm clearing it. Okay, it's done.
Yeah. Okay, yeah. So you can see that they're all meeting at the focus. So the image is formed at the focus. So just to make it easier, you can start it from directly from there itself, because otherwise you won't have a logical in reflecting point. Now the angles are now will be equal, because it's basically the same deflection, because it's all from the focus. So the image is formed at the focus, and you can get the correct reflection method as well. So basically just make sure that your reflected ray and the focus, it's on the same plane. That's on the same line basically. Yeah, just keep that in mind. So basically, as Khadir told, the object is at infinity, so the image is formed behind the mirror at f. So you can see over here the dotted lines, and it's also highly diminished, point size, virtual, erect,
and erect. Erect means straight.
Really, like it's on a dot, so it's point size as well. But you can write diminished, so that's enough.
Okay, so
Clear
let's
the
do the
screen.
next one.
Yeah. As you
Just
clear the
erase
screen,
this element.
you can try. Okay.
Yeah.
I think you need the principal axis for this. Yes.
Yeah,
You
and
do.
I'll draw. Don't worry.
Yeah. Take.
108. Okay, see, you do. Okay. So let's keep the object at the same place, which is here. So the first ray, it will go on top like this, and then hit the mirror, and it'll go okay, and it'll reflect over here. But it will what do you call come here. Now, because I'm using this arrow, I can't make the dotted lines. That's the reason. Okay, 1 minute. I'll just make it proper. Wait. Okay. 1 minute. See. Wait. Aman, wait. Aman.
Hey, what
Yeah,
happened?
Aman. I can't draw. Anon it went. Oh, it came back. Coming and going back again and again. See this one. Aman, can you just what do you call it? Erase the FNC over here. I'll just make my own FNC.
Okay, fine.
Okay, fine. The first tray over here. First tray over here. Pass to the top. It hits the mirror, and it diverges outside. So there's no point. It won't what do you call meet any other ray. And the second mirror, second ray, it goes like this, and it hits this, and it goes back the same way. Goes back like this. Same. So these both rays don't diverge at any point, but we have to make this rays diverge. So we bring them in like this, and this, and they meet at a point which is F. I will draw it. This is the F point. This is the focus. So they meet at the focus. Do they? But am I wrong? Oh no, but I'm wrong. Oh, they don't meet at focus. My bad. See, the first ray, it what do you call it? It goes to the focus, and the second ray, it meets at the center of curvature, which is here. Focus and the center of curvature. These both points are meeting over somewhere here, so the image is formed over here. In this case, the image is diminished, virtual, and erect, same as the other one. In convex, yeah, in convex mirrors, the images are always diminished, virtual, and erect. Diminished means small, virtual, and erect.
Okay, so I'm going to clear the screen now. Okay. Fabio, can you try to draw one of the ray diagrams if I tell you to? Like anyone, I'll just give you all the conditions and can you draw one? I'll erase the screen. You can use the annotate option. 1 second. I'll just yeah. I'll draw you the mirror. Can you just do the rays and stuff? I'll draw the mirror for you. Okay, is it fine?
Okay.
Yeah, okay, fine. Nice. Yeah. That's it, right? Yeah, focus and center of curvature. Yeah, you can try. So the condition is at no. Okay, at pole. Okay, no, between pole and focus. Okay, and focus, and yeah, that's it, right? Just have to place a bit. This is the pole. Okay, this is the pole. This is the pole. This is the focus. So you can try now.
Between pole and focus.
Yeah, pole,
Okay.
pole here, focus here. What will happen?
Actually, I'm using tab. It might be a bit sloppy, actually.
No, no, it's fine. It's fine. Just to see if you understand. It's fine. It's fine.
Wait 1 second.
Fabi, you tell us, we'll draw for you if you're having problem.
No, no, it's fine. It's fine. Let him try.
So, between pole and focus. So far, is it okay?
Yeah, I'm making a duck. What are you doing? I'm making a duck.
Yeah, it's perfect. It's perfect.
Wait. Wait 1 second. I don't know how to do like the line by line. Yeah, it's supposed to intersect somewhere over there.
That intersects here.
So this is perfect. It's the correct. Okay. Okay. Shit. 1 second. It's the other way around. Yeah. Perfect. So that's the first one. Now, Ayan, can you try one? Let me just clear the screen. Okay. No. Yeah, Ayan, can you try?
The same thing, which one?
No, I'll give you another one. Okay. Bit more easy, I think. Should be easier. Let me just erase everything. Okay. 1 second. Oh yeah. Yeah. Okay. So over here it is. Beyond C. Okay. Beyond C. That's it. That's the condition. And just tell the nature of the image. Okay. After you're done. So yeah, everything's already there. So you can start. You won't need this now. You don't need this. How did that? Okay, fine. You can start. Beyond C means it should be away from C. Like, remember, right? It should be
Or infinity. Beyond C means here.
like anywhere. Yeah, perfect.
See, it's here. Infinity means here. We already explained. Don't confuse. Ma'am will remove deduct marks if you do this, and the image will form wrong.
Wait, is it? Okay, fine.
So the object, we made the object. I undo it.
Okay.
Okay, yeah, that's good. And the live?
I don't know.
Yeah, it's perfect.
Yes, correct. It's correct.
Now, what is the nature of the image? Can you tell?
Is it like inverted? No.
This is your
See,
image.
I'll remind you. Okay.
This is
It's
the nature.
inverted, no.
In it's inverted, correct?
No, it's fine.
Inverted
Let
I.
him try.
No, he told inverted. He told.
What he told?
He told inverted.
Inverted. Okay, there's 2 more. Just try. 2 more is there.
Real, inverted, and
and
Diminished,
yes,
or I don't know.
correct only. Rate
Real,
inverted and
inverted, and diminished.
yes, correct. Okay, so
Aman, why do you remove me again and again?
I'm trying to clear the drawings.
I can't do it.
One sec. It's fine right till here. So this is the ray diagram for mirrors. You can draw now. It's not needed anyway till now. For now, it's not needed. It's probably come back. Okay. So everyone is fine till now. You can draw. Yeah, I can draw. So everyone should be able to draw. Okay. So okay. Basically, that was the ray diagrams for mirrors. So that is a part of the topic over. Now the second part of mirrors is it's numericals. So before that, you need to know some sign conventions. Okay. So this is just to make you understand how to take the signs for rate like numericals. They won't include negative signs. For example, your object is coming over here. Okay, wait, let's just take the diagram. Your object is coming over here in the ray diagram. So it's on the left hand. No. 1 second. I'll take a concave mirror. It'll be easier. Yeah. So here your object. This is the virtual case. Okay, whatever. So your object is here, right? So it lies towards the reflecting side of the image, like not behind the image, it's in front of the image. I mean the mirror. So it will always be negative, right? But in the question, they won't give -2 centimeter as your object distance. They will give 2 centimeter. So this is how they'll give, but you should know that you should be marking it as u is equal to -2 centimeter. Now that is just to like bring a beginning. Now we'll go through all of them. So these are the sign conventions. So in the sign conventions, the pole of the mirror is taken as the origin. Now everyone remembers this, right? One second. Let me take the arrows. One second. Does everyone remember this? Like, anyone? What is this basically?
Plane.
Cartesian plane, right? The one
Yeah,
we used to
Cartesian
math
plane.
coordinate geometry. We learned, right? Cartesian plane, right?
Yeah.
So now they're merging physics and maths over here. We are merging the same thing. Okay, now let me take the pen. I'll draw the stuff and show you. Okay, each and every point we'll go through now. We just take the pen. Okay, so yeah, this was our Cartesian plane, and
This is minus x.
this is x. So just mark it x and x dash, not like that. Just mark it x dash, y dash, y dash. Okay, done. Now, if you remember, this was the positive side, right? Everyone recalls, right? No doubt. These two are the positive sides. 1, 2, 3. Numbers are not required, it's just to show you, so might not be able to draw it right properly. -1, -2, -3, -4.
Just make points, you'll understand.
-1, -2, -3. Okay. So this is how the Cartesian plane is, right? Everyone understood? Right?
Yeah.
Yeah, right?
So
now,
what is this?
Yeah.
What is telling that even in this mirror, the objects, everything that's on the left side will be denoted as a negative sign, and which is on the right side will be denoted as the right hand sign.
first of all,
just merging-
look, I'll just tell properly, okay? Just listen to this. This point over here, this is the pole, okay? So just imagine that there is a mirror over here, okay? This is how you have to imagine it. The mirror is like this. Your pole is over here. Like basically this point, I can't write over here. This is the pole, and your object will always be on the left hand side. You can all agree to that, right? It's a concave mirror. Everyone can agree, right?
Object will always be negative.
Yeah. So it will always be the object distance will always be negative. So, but the light is always fall from the left hand side. The light will always. This is the ray of light. It's coming. Suppose it's coming from the sun rays. So this ray of light will always come from the left hand side. Okay, object is placed left on the left side of the mirror, and the light from the object falls on the mirror from the left hand side. And all distances parallel to the principal axis are measured from the pole. Same thing. It's parallel. This distance over here, this distance is parallel to the principal axis, and it is measured from the pole. This one. And the third one is all distances measured to the right of the origin along plus x-axis are taken as positive. Suppose if we have the case where you have the last case when the object is placed between, like over here. If this is the case, then your object will be formed over here, right? And when the object is formed over here, the distance from the pole and this object will always be positive.
Positive.
And on this case, it will be negative. So all distances measured
So
from to the right of the
whenever they
origin.
ask you to take the distance of incident ray or a reflective ray or distance towards the from the object to the pole, always take it as negative.
Yeah. So yeah, basically that. Now the third and fourth one, let's just do it together. Okay, one second. Let me just draw it. I'm clearing the
Clear a
screen.
bit,
I'm just clearing the
clear it.
screen, okay? Okay. Oh shit, everything went.
So
Okay, let's just take
distance
this one. Let's just take
measured
this one.
perpendicular to
So
and above the principal axis are taken as positive.
yeah, so over
Same
here you
thing, the
can see
top
that
and bottom.
like this is the pole, okay? Everyone can agree, right? So this is the pole. This is perpendicular to and above the principal axis. You can see that this is perpendicular above the principal axis. This is the principal axis. It's above the principal axis. So we take this as positive. We can all agree every like there is no case where the object height will be negative because you can't just place it inside it. It will always be upright. Okay, now suppose if you don't take it in this way. Suppose if I have a what do you say, if I have a cup, you know how we usually hold it, right? Now just because I hold it upside down, you don't tell that it's inverted because you're holding it like that. It's still straight, it's still positive. You can't call it inverted because that's how you're holding it. Inverted means the image can be inverted, not how you hold it. Now suppose if you hold a cup upside down, its image in a concave mirror, its image form will be upright like the normal way you hold it, but that's the image, okay, if you hold it. So just because you're holding the cup upside down, that doesn't mean the object is at inverted position. You're still holding it erect, but it's only like I'm just trying to explain that point. So over here, when the object is upright on the principal axis, it's always positive, and when it's inverted, it's negative. So that's it. No doubt, right? Everyone understood? Yeah, basically we'll be going through questions. That's how you understand this more. One second. Yeah, Kadir, you can start now.
Yeah, okay. So now we'll learn numericals and the what do you call the what we denote things with. So first over here in a spherical mirror, a normal mirror, the distance of the object from its pole is called the object distance. That's obvious. See, this is the what one. Okay, so this is the plane, and suppose this is the mirror. I'm not drawing the curve. This is mirror, and the object is here. So the distance here between this and this is called the object distance. And the distance of the image means the image or here. Sometimes the image is formed here, sometimes the image is formed here, or up here. So the distance of image, let's suppose this time the image is forming here. So distance of image from this is called the image distance. And the principal focus is called what do you call it? The distance of the principal focus from the pole is called the focal length. So we all know what is focus. Focus is here, is the center of curvature and pole focus, and the distance from the principal focus and the focus is called the focal length. So basically, in this here, this is the focal length. Now next, yeah, and one more thing. To find this is what we call a relationship between the object distance, image distance, and the focal length. It is 1 by u plus 1 by v, 1 by v plus by 1 by u equals to 1 by f. Usually, suppose we have the object distance 5, so we'll take it as 1 by 5 plus image distance 1 by 6 equals to 1 by f. Okay, so in this case, we'll get, or let's take this also as 5. This will make it easy. So we get 1 by 10. 1 by f equals to 1 by 10. So in this case, the focal length will be 10.
Don't forget
That's
to
it.
take the reciprocal for both, or else the answer
Yeah,
will
you
be
have to take the reciprocal for both. So
just
f
like that
goes here
electricity
and
thing.
10 goes here. So focal length equal to 10.
So you
Okay, I'm
remember
on
the
next.
electricity thing of parallel? Just remember same thing. Just you have to take the reciprocal. We have the next
Yeah,
one.
okay, next one.
Like magnification.
Okay. Magnification, we all know magnification is when an image is magnified so we can see it more clearly. Uh, okay, so magnification is denoted by M, and there are two ways in which we can, what do you call, get the magnification of an object, of an image. The first case is the height of the image by the divided by the height of the object. So height of the image is, we can just, I don't think there's a specific we don't denote it by a specific letter or something. We just said height of the image by height of the object. In this case, they just wrote h comma h hyphen and h.
Right, height of the image, height of the object. That's it.
Yeah, that's it. There's no special letter or something. So this is just just explaining to you guys.
So you can write this.
So so suppose the height of the image. Where's my pen go? Suppose the height of the image is 10, and the height of the object, our real object, is 20. So when we divide 20 by 10, we get 2. So the magnification is 2. That's it. That's as simple as that. But in some cases, they might not tell you the height of the image or height of the object. In that case, magnification can also be denoted as minus v by u, right, Aman?
It's coming.
Aman?
Yeah, it's coming here.
No, it's minus v by u, right?
Yeah, it's coming. It's coming. Yeah.
Minus v by u here.
Like in this case,
Minus v by
suppose
u.
if I take, suppose if my, in this case, okay, over here it's given h dash as height of image. So if height of image is 5 s, you have to find the height of the object, and you have your v as 2 and your u as 4. U as minus 4, it will always be negative. Even this will always be negative. Just keep that in mind. It will always be negative, except the case for convex. But over here, let's just take image distance also as negative. It will be 5 by h is equal to minus of minus 2 by 4. This is 4, okay. 4, yeah. So it will become 5 by h is equal to 1 by 2. Okay, get it right? It's 10. So we'll be going through questions just to give an idea. So height of object is also 10. So magnification is related to both height of image, height of object, and also object distance and image distance. So next one. It's a question. So we have two questions. So first one, let me just go through this, okay? So object is kept at a distance of 4 centimeter in front of a spherical mirror. It forms an image, erect image at a distance of 1 meter from the mirror. Okay. So we have to find the magnification. Now for magnification, you know that the formula, like first of all, you have to check which mirror it is. It's given that it's a spherical mirror, but it's also given that it forms an erect image. So which image can it be? Can anyone tell? The answer is on the screen. Just tell someone tell.
Convex.
Convex mirror. Yes, correct. So let's go. So the formula remains same for both. It's minus v by u. Over here, v is given as, what is it given? Which forms an image. Image distance is 1 meter. Minus 1 by, object distance is given 4 meter, but we know that it's always negative. 1 minus 1 by minus 4 is equal to 1 by 4 is equal to plus 0.25, or you can write it as 1 by 4 itself. Anyway, you can write it as anyway. Okay, so magnification is positive. So at this point, it should be obvious. So look, I'll give you a couple more cases, okay? Just observe these cases. Over here, magnification is 0.25, right? Except the last case, what would the magnification be for a concave mirror? Anyone can tell? Except the last case. Magnification, like, any idea?
Minus magnification.
It will be towards the minus side because it's inverted. Now, what if it's at C? Like, except at C, because at C the one, it will be minus 1 basically, because it's inverted, but then it's inverted as well, but it's the same size, so it will be minus 1. But as you now, in the case of what do you say, the erect images of concave mirror, was the image bigger than the object, or was it smaller than the object? The erect case of concave mirror, was it bigger than the object or smaller than the object? This one. This is the focus. The object is placed over here. Is this bigger or smaller? That's a bigger or smaller?
It is small.
No, it is bigger. This is the image. This is the
What are you
object.
talking?
Yeah, the image is small.
Hello?
So bigger, right? So we know that magnification is the
Can't hear you.
factor, like the number by how much it is increasing, right? So in the case of concave mirror, the magnification will always be higher than 1, right? Because it should always be bigger than the object. See, we checked. I told you about the case where it becomes -1. It's the it doesn't matter. Leave the sign for now. It becomes 1 when the object and image are of the same size. But over here, the object is smaller than the image, so the magnification should be positive. Not like that. The magnification should basically be more than 1. So over here, it's less than 1. So this proves that it's diminished, like it's smaller than the object. Hence, it's a diminished image, and hence it's a convex mirror, because in convex mirror image is always erect, so that's why it's positive. Also, image is always smaller than the object, so it's smaller than 1. So just 2 points you have to keep.
Okay, let's go to the next one. How many more slides are remaining?
A couple of them. This is dude.
No, okay. A 4.5 centimeter needle is placed 12 centimeter away from a convex mirror. A focal length 15. Okay, let me just draw this over here. God.
You have half the chapter left, so go fast.
Okay, this is this stuff. Mirror is here. 4 centimeter needle is placed 12 centimeter. Needle is here. 12 centimeter away from convex mirror. So this is wait, 12 centimeter away. Focal length is here. Let's just keep the focal length here. 15 centimeter. Give the location of the image and magnification. Describe what happens to the image as it is moved away further from the plane. So wait, I made a mistake over here. They said that the image is 12 centimeter away from a convex mirror and the focal length is 15. So now if the focal length is 15, which is more than a minute, so the image should be in between focal length and pole. So let's make this the focal length, this one. This is the focal length, okay? And this is the image. So the image should be here. Fine, can you guys see? Okay, yeah. So focal length is here. So this is 15 centimeter. This is 12 centimeter. And now we know that if the when the image is between focal length and the pole, the it passes through this, this, and this. This. So image is formed between focus length and pole. Wait, here. Yeah, so the image is erect, diminished, and virtual. Okay, now let's do the what do you call it? The
So you don't
formula.
need to draw ray diagrams. We can just giving it, like, yeah, when they ask you, you have to give, obviously, but then when you're just normally doing questions, you don't need to draw ray diagrams.
Yeah, fine. Okay, let's skip the ray diagram. So we have to first find the what do you call it? We have to find the image. What
You have to find the
so one by we know that
magnification,
focus
object height,
yeah.
and this thing.
The
Image.
object height, how we find it, 1 by 15 plus 1 by 12 equals to 1 by v. So we get it 6.6 centimeter after doing calculation that you can do later, because we don't have time now, we'll just skip it. And magnification, we know height of the object by height of the image, or minus v by u. So over here the magnification we get after calculation is 0.56 meter plus. So that's it. We have gotten the magnification and we've got the height of the object. Next someone.
Perfect. So now, so this is half the chapter. We reached half point. It's taking much more time than expected, but then we have to finish this anyway. So it's something you have to do.
So,
you can try this out.
So Aman, let's just skip some questions.
Only one question is there. There's 2 questions.
Well, let's skip it. It's fine.
Try it out. Yeah, be responsible. Everyone try it out. It's obviously useful. You can try it out.
Aman, I have to go out 4:45, so I don't know.
Oh.
Hello?
Yeah. One second. Okay. You guys can try it, but then I'll solve it, okay? So now that I've taken, I'll quickly solve it then. Okay, it's fine, right?
Let's solve it.
I'll
It's
just
taking
solve
so much time.
Okay, so one second. Let me just take the pen. height of object is 2 centimeter. No one can see it, right? Okay. Focal length is 15. Okay, focal length will be minus 15 since it's a concave mirror, and the object
there's it.
distance is 30 centimeter. Okay, now let's find. We are asked to find the nature of the image, the size of the image. But for finding the size of the image, we know that the relation is magnification is equal to minus v by u. So we need to find v. What is this? What is that? Okay, anyway, 1 by minus 15. 1 by minus 15 is equal to 1 by v minus 1 by 30 minus 30. So we have 1 by v is equal to 1 by minus 15 plus 1 by 30. So everyone find till here? No doubt, right?
Yeah, Aman, I think I have to go by 4:30 now.
Okay, what? Okay, sir. I'll try to quickly move, okay? Let's try.
Yeah.
30. So basically you will get v is equal to minus 30 by 3, I think. Yeah. One second. Let me just quickly check it, okay? Just to make sure that I don't do anything wrong.
V is minus 10.
What? This is minus. That's what I knew something was wrong. This is minus, okay?
Yeah, V is minus 10.
Yeah, so you get minus. Yeah, minus
2 minus 3 will be minus 1, right? So V is minus 30 by minus 1.
Yeah, so we have
which gives you 30.
30 centimeter.
That's the next magnification. So magnification will be 30 by minus 30 by u, which is minus 30. Magnification is 1.
Wait. 2 minus 1 by 30, that will become 30 by minus 1. Minus 30 meter. Just keep it in mind. So this is how we know that you made a mistake. It will always be negative. You know that your image distance is always negative. So that's how you can keep it in mind. So you see how we found out that we made a mistake, right? So yeah, just keep that in mind as well. So we found out that our image distance is minus 15. Let me just erase this quickly. Okay. So now we're getting to the point where we're supposed, like, what we're supposed to solve. So we know the relation that. One second. Let me just. Why isn't it moving? Yeah, I can't write what happened. Okay. So we know that there's a relation m is equal to minus v by u, right? Is equal to h dash by h. You have to write height of image by height of object. Okay, I can't right now though.
Yeah, okay. So
Minus of minus
30.
30 divided by the bracket. Minus of minus 30 divided by where is u?
That will be plus 30 by minus 30. So it will be. So this cancels minus. The answer will be minus 1.
Dash by 2. You will get minus 1 by 1 is equal to h dash by 2. H dash
H equals to minus 2.
Minus 2.
H dash equals to minus 2.
Now we are asked to find the nature of the image. So over here you can see that there's negative sign. So from this you can understand that the image is formed below the, what do you say, the principal axis. Also, height of the object is 2 centimeter. Height of the image is 2 centimeter. So the object and image size are equal. So magnification will be 1. So it's same size. Object size is same. The image formed is real and inverted. That's it. That's your magnification.
Okay.
Next, quickly. Yeah, ray diagram. You can check the ray diagram. Let me just clear the screen for you all. That's a ray diagram. You see the same thing. You don't need
to just skip it.
Yeah, you don't need to draw it. Just keep this in mind. Okay. Next one. One second. Let me just clear the screen. I'm disabling annotation features. I don't know. I'm seeing random stuff. Yeah. Okay. Next one. Refraction. So refraction is the phenomenon of bouncing back. I mean, the change in path of light. It's the bending of light. Not bouncing back is reflection. This is the change in direction or the change in path of light in going from one medium to another, or the bending of light. Over here, the incident ray is going like this. It's bending towards one direction. It's not reflection. This is reflection.
It's like a glass prism.
It's basically bending towards it. So now the difference between refraction and reflection is that refraction takes place in two mediums. Over here you can see rarer and denser medium, while reflection was only one medium. So basically, why this happens, I won't be like, we won't be going into this topic because it's not related to today's topic. Just giving you an idea, the refractive index of air is like, air and glass are different. Like suppose if air is one, it's not one, okay, it's not even close to one. If air is one, it is, I think it's one. Actually I think it's one, and glass will be two. Okay, so if air is one and glass is two, you know that the refractive index is different, so it will bend. That's the reason why it bends. While in, if this is one surface and reflection takes place, then it's the same medium, it has the same refractive index, so it's bouncing back in a medium of the same refractive index, so that's why it's not bending anywhere. Now just to give you an like this same, just to give you an idea, incident ray, when it's going from rarer to denser medium, it bends towards the normal. This is the normal, and it's, this is how it should go. Okay, this is the like the incident ray is traced backwards, but it's moving towards the normal. And the other one, it would move away from the normal. So suppose if this was glass and this was air, then the incident ray, it would go like this. This is the normal, this is the traced back incident ray, it's going away from the normal. Yeah, that's this, that's that. Next, laws of reflection of light, refraction, not related to our topic, so let's just quickly go through it. Okay, the following are the laws of refraction of light. Okay, as you saw in the previous one, the incident ray, yeah, that's a normal. Okay, it's not straight, it's not at all straight, just observe it from the 90-degree. So the incident ray, the refracted ray, and the normal, this one, normal to the interface of the two transparent media at the point of incidence, this point of incidence, they all lie in the same plane. They still, even the other case, they all lie in the same plane. The second one is the other a bit more different one. We don't know this. The ratio of the sine of the angle of incidence by the ratio of the sine by the sine of the angle of refraction is a constant, and this constant is known as refractive index. So it's constant for a light of a given color and for a given pair of media. So if the pair of media or the given color changes, then this will also change, and this is known as Snell's law of refraction. None of this are included in today's topic, so let's just quickly move on to the ray diagrams. So yeah, Khalid.
Yeah, okay. Formation of ray diagrams in lenses. 1 minute. Okay, yeah. Okay. For drawing ray diagrams in lenses alike or spherical mirrors, we consider any two of the following rays. A ray of light from the object parallel to the principal axis after refraction from a convex lens passes through the principal focus on the other side of the lens. In case of concave lens, the ray appears to diverge from the principal focus located on the same side of the lens. So what they're telling is, in the case of convex lenses, again in this case it's the opposite. Or let's skip it. Let's listen to this. So the after the rays gets refracted, it passes through the principal focus on the other side of the lens. And in concave lenses, it diverges on the other side of the lens. So we draw a dotted line structure back, which also passes through the principal focus. This is the first one. Next, Aman. Okay, a ray of light passing through a principal focus after refraction from the convex lens will emerge parallel on the to the principal axis. Okay, wait. Aman, can you enable my that thing?
Yeah, it's able because someone was drawing. That's it. Yeah.
Yeah. Okay. Okay. Oh, here in this case, you can see here the ray of light is parallel to the principal focus on the other side, but when it's passing through the focus in a convex lens. But in a concave lens, when the ray of light uh, when a ray of light just comes out of nowhere, I don't know from where it's coming, when it passes through the lens, it is also parallel to the principal focus. In both the cases, in this case, the ray of light at some point meets at the focus, principal focus. Next one. Okay. Uh, um, a ray of light passing through the optical center of a lens will emerge without any deviation. Optical center means the exact center of the lens, in this case O, in both the lenses. So as both the lenses have an optical center and it doesn't make a huge difference. So the ray of light passes through like this and comes out straight in both the cases.
Any doubt? All three, same thing. It's basically the same thing if you compare the other thing, but it's just that the ray passes through the other side of the mirror now. And just
Yes.
keep in mind that when you're drawing the ray diagram of a lens, you will have two focus, two center of curvature, and one optical center instead of pole. Yeah,
And
just keep that in mind.
yeah, next,
So ray diagrams. Okay,
convex and lateral. Okay.
gonna be really
When the
one second, just quick.
or Aman, we'll just explain with the picture over there and this.
No,
This will
we
take
have
a lot
to
of
do
time.
it. We have to do it.
Okay, fine.
We did it for good mirror, so we have to do it for this as well. Quickly do it. I'll quickly do it. Oh god. Oh god, that's messy. One second, one second. Okay, so basically, when the object was at infinity in the case of mirror, where did the image form? Does anyone recall? It's a bit sloppy, but then just ignore it. Does anyone recall where was the image formed when the object was at what do you say, infinity in the case of concave mirror? Fabio, can you tell?
We at for concave mirror, when the object was at infinity, image was at focus.
Yes, that's what. So it was at focus, right? Now I'm going to do the same thing. I'm just going to repeat the same thing. See if there's a pattern, okay? But this is convex, okay? That was concave, this is convex. Let's check if there's a pattern. The incident ray, drawing a parallel line to the principal axis and it's passing through the focus. Drawing another line parallel to the principal axis is passing through the focus. And this is already a parallel line passing through the focus. So where is it formed? Where's the image formed? Where's the image formed?
Focus.
Focus, that's what. So same thing. You remember the last case, it's the same thing. The image is point sized, it's real and inverted, it's diminished, highly diminished, it's really point sized. You can see the intersection point. And yeah, it's formed out behind the mirror at f2, all this kind of stuff. Next one. Yeah, again observe for the pattern. This is going to continue. Okay, so okay, wait, that's not the arrow. Okay, so we have our beyond C object, parallel line, pass through focus. Okay, so now we will take the one where it passes through the optical center. Okay, so yeah, we can't take two times the same thing, right? That's why I just took another one. So yeah, that's how it one. So this time it is formed between the center of curvature and the focus. It can, as I told you, it's not necessary that it has to be exactly between, because that's completely not logical, because you can place it anywhere. Like you have beyond C means you can like, it depends on how much you extend the principal axis from here to here, like from here, from this point over here to this point over here. You can place this object anywhere you want because all of them are beyond C. So according to that, there's obviously a variation in where the image is formed. So just keep that in mind. It does not obviously have to be in between. Do not measure it. Your answer will be right if you get it in between F and C. Yeah, that's the first thing. Again, you need to draw the arrows and stuff. Just keep that in mind. Yeah, all this kind of stuff. Okay, so it's diminished point size. It's not point size. It's diminished, real, and inverted. It's obviously not point size. You can see it. The image is visible. Next one, at C, at 2f1. Okay, so over here we don't call it center of curvature. You call it 2f1. Let me just change that. It's a small error. It's 2f1. Okay. F1, 2f1, 2f2. Okay. So we're talking about the case where the object is placed at 2f1. You have to especially be careful about this calculation because the other ones, it's like, it's not, you don't have to get it at a specific point, but you have to get this one at a specific point with same size and same position. You're gonna see why. So this is our first ray, this is the second ray. So over here you're seeing that this always has to be a straight line over here. So from here, this point, right, it should always be a straight line, and this one you should measure. This one you should measure, because if this is, if suppose if the object is 2 centimeter, then the image has to be 2 centimeter. Now it can't be 2.5, it can't be 1.5, it has to be 2 centimeter. and it should touch the point of intersection. Now look, okay, now suppose it intersected over here. You don't try to join it like this, okay? It's much better you try it again, because you're not going to get a mark. It has to be touching the point of intersection right to the to F2, and it has to be straight, like it should make 90 degrees, okay, with the, what do you say, principal axis. It's real inverted, same size. Yeah, it's real inverted, same size, and all that stuff. Next one, it's play when the object is placed in between two F1 and two F2. So, yeah, 2F1, 2F2. You can see, you should be observing that I'm using the same rule again and again. The one that passes through, oops, oh, that's not, I didn't try to do that. Okay, the one that passes through the optical center, and the one that, yeah, one that passes through the focus. Does anyone have doubt here? Any doubt? That's it. That's basically it. Is formed beyond C. You can see that the, one second. Yeah, you can see that the object is formed beyond C. It's much bigger. Not, yeah, it's enlarged. Basically, you can see that it's much more enlarged, and it's inverted. It's facing, the arrow is pointing downwards. It's inverted. It is real. Yeah, got the point, right? Any doubt? All right. Okay, fine. So this is the last one, which the normal cases. Out of the normal cases, this is the last one. So, Ayan, can you recall how the image was when the object was placed at focus? Just recall. When your object was placed at the focus in the case of a concave mirror, can you recall how the image was formed?
Well, diminished.
Where was it formed? Where was it formed?
Uh,
Object is placed at focus. Don't you remember, it touches like over here and goes over here, next one goes over here. They never meet. So it was highly enlarged, right? It's not parallel exactly right now, it's just rough. So it was highly enlarged. So let's see what happens here. They never meet because they're in, no, they're parallel, they will meet but at infinity. So that was the case in concave. Let's check what happens in the case of convex lens. Same rule, we are using the same thing. Okay, one second. Yeah, don't draw it this way, okay? I was not getting the parallel line, that's why I drew it backwards. So you can see that they're never meeting. They're kind of parallel lines, right? They're all parallel. The same rule we use.
yeah,
They are parallel lines and they'll meet at infinity. Sometime they'll meet, okay, but we can't show it because it's infinity. Since they will meet, we can say that the image formed is, it is formed, it's real inverted. Okay, now suppose if this is infinity, this region is infinity, and I drew an object. This is the image of the object. You can see that it is inverted, it is real, and it's highly enlarged. This is the object and this is the image. Now this is not infinity though. You know where infinity is? Like you can't even, like, it's something that you can't measure. So when it's formed at infinity, the image will obviously be highly enlarged, much bigger than the object, and it will continue to be inverted and real. So the last special case, we had a special case in the case of concave mirror. We have one in the case of convex lens too. Okay, so the okay. Oops, this one. So in this case, the object is placed between focus and pole. Not pole, optical center, okay? So one second. First of all, I'll show you why you can't do it in the normal way, okay? So why can't I just do it like this? Can anyone tell? Anyone can tell. Why can't I
won't be
just do it?
parallel.
They are not parallel lines, right?
Yeah,
Yeah, so they'll never meet. But then according to the logic of physics, or you can tell the teachings, like whatever we have learned in physics and maths also, compare it to maths also, parallel lines will meet. So we know that an image is formed. That's why ray diagrams are for. We should form an image, but in this case, you can't form an image. So why are we drawing a ray diagram in the first place? We have to get an image, right? So since you can't get it in the normal way, let's try to trace it backwards and get an image. So this is how it will go. The second one, something like this. and you have a straight line object. Can you see? Same thing. So it's not necessary that it should always form in this in the at 2f1. Somehow even this it's 2f1, but then it's not necessary. It can form anywhere depending on how you like what do you say, your rays and all are. But you can understand that. Okay, now one more thing is that this should be dotted. Okay, because the image is not actually formed. It's just you're making it form by tracing it backwards. It's not actually formed though. So that is your image, and this is your object. When you're tracing it backwards, you're getting your image. So since it's formed on the same side of the image, this time it is virtual, it is erect, it is highly enlarged. Again, it's really enlarged. You can see this is the object and this is the its image. It's enlarged, virtual erect, and it's formed on the same side of the lens. So that was the convex lens. Now concave lens. So first of all, the lens itself is a bit it's going to be tough to draw here. 1 second, let me just quickly erase this. Yeah, 1 second, 1 second. Oh god. Oh god. Yeah, fine. Oh god. Somehow. So that is your concave lens. Now this is your focus. This is your 2f1, center of curvature. 2f1 can also be written as c1. Okay, but usually we write it as 2f1. Yeah. And make sure that, look, okay, just make sure. Now suppose yeah, the distance between 2f1 and f1 should be equal to the distance between f1 and o. It should be equal to the distance between o f2, and that also should be equal to the distance between f2 and 2f1. All 5 points should be equal. So if this is 2 centimeters, this should be 2 centimeter, this should be 2 centimeter, this should be 2 centimeter. Just keep that in mind. Okay, now first case, object is at infinity, images formed in the focus on the same side of the lens. Okay. Oh no. So this is the object and it's the parallel line. Now, okay. Now, how should I continue? Just how should I continue? Can anyone tell? How do I continue this? Can just recall the convex mirror case. How do I continue? Anyone can tell? Fabio, anyone? Where do I construct it? Like, where do I continue? Which side should I go? You don't remember? So I'll just recall it once more. So you keep your scale at the focus. Okay. Touch this point over here, the point where it reaches right in the middle of the lens, and you just draw a straight line. Make this dotted, by the way. It should be dotted till the intersection point. It should be dotted. Similarly, you can draw another one. Okay, let's just make this a bit more big. Okay, let this be this big. So you can draw another one over here. This will go like this, and this one will diverge to the other side. So you're seeing that the image. So just take one straight line as well. Just take one straight one as well. Okay. You're seeing that the intersection point is on the same side of the lens. It is point sized, diminished. It's also virtual and erect. So yeah, all the kind of stuff is there. Next one is when it's placed between infinity and the optical center. So when the object is placed anywhere, okay, so we don't actually need this since you can draw it. Obviously we need it, but then in this case, I'm just to make it easier to explain, you can keep your arrow anywhere. You can keep it here, 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 anywhere you can keep it. So let's just take it over here. Okay. So the first one, it should be like this, right? Yeah. So let's just take the focus since we need the focus to show the refraction. So yeah, that's your focus. So the first one would be going like this, right? And you make this dotted.
Aman, I have to leave the class, okay?
Okay, I'll quickly finish this one. You all remember the rule where if a ray of light passes through the optical center, it goes on without getting deviated, right? It will go undeviated. So you see that the image is formed here. It is virtual, erect, and diminished. Is everyone fine with this?
Yeah.
Okay, so that's the ray diagrams. So both the ray diagram sets are over. Okay, that was good. Now the next one, the numericals, same thing, okay, except the minus part. Now over here, for the lens formula, we have it's a relation between image distance, object distance, and focal length. Same thing, but over here you can see that it's minus instead of plus. And for the magnification, it is the same thing. It's the magnification for lens is also defined as the ratio of the height of the image to the height of the object. It is defined as h dash by h, that is height of the image by height of the object. And over here there's a difference though. We write magnification for lens as v by u. In the case of mirrors, it was minus v by u, but over here is just v by u. So we saw two changes. Over here, this was supposed to be plus. One second. This was supposed to be plus. This is plus in the case of a mirror, but over here it's positive. I mean negative. And over here, the magnification for mirror, it was minus v by u. Over here it's v by u. So yeah, let's just quickly go through this. So here image distance is given as minus 10 centimeter, focal length 15 centimeter. We have to find the object distance. So use the formula when after we calculate, we get u is equal to minus 30. So the object distance is minus 30. And we know that the formula of magnification is v by u. So it will become minus 10, v is minus 10, u is minus 30. It will become 1 by 3 plus 0.33. Now another reference from what I had told before, for concave lens, the image is always erect, so magnification will always be positive. Also, if this is our concave lens, this is the image, this is the object. I mean, this is the object, this is the image, okay? This one, this is the object. So the object is bigger than the image. So the magnification should always be less than 1. Also, the image is erect. It's above the principal axis. So it will be positive. That's it. So your nature of the image is erect, virtual, and 1/3 the size of the object. That's it. Next one. Almost over, almost over. A 5-meter tall object. So your height of the object is 5 centimeter, focal length is 20 centimeter, and object distance is 30 centimeter. We have to find the position of the image, nature of the image, and size of the image. For size of the image, you can calculate both magnification and height of the image, h dash. So one second, let me just move everything, okay? So here we have object size is 5 centimeter. Yeah, everything we have discussed. So after using the formula and calculating everything, you get that your image distance is 60 centimeter. Now we have to find the size of the image. So we found the position of the image. The position of the position is 60 centimeter. Now the size of the image, you're taking the third one now. This is the third one. Okay. For your third one, you have m is equal to v by u is equal to, where's v? V 60 by minus 30, that will become minus 2. Now again, reference from the previous what we have learned. This is a convex lens. This is the object. This is the image. First of all, you can't take it in the same way as convex, because you don't, for concave lens, the image will always be smaller than the object. But for convex, you can't see. But one thing you can say is that it's always formed below the principal axis if it's not the last case. So you can't always tell again. You have to look at this, okay? Over your focal length is given as 20 centimeter, right? And object distance is given as 30 centimeter. So the object is placed not between the pole and focus. So it will be negative. The image will be inverted. So your magnification will also be inverted. I mean minus. So, but if this was 15, if this was 10, what would happen? Can anyone predict the magnification? Like, can you just tell it's positive or negative? Can anyone tell? Ayan, can you try? Will it be positive or negative?
Yeah.
If it's placed 10 centimeter. Yeah, positive or negative? Any idea?
Positive.
Positive, yes, it will be positive because when it's a last case. So this is the last case because the focal length is, so this is the lens. This is optical center. This is focus. So if the focal length is 20 centimeter and the object is placed at 10 centimeters, so it's between F and O. So it will be the virtual case. So that's why it will be positive. So that's the first thing. Now magnification is equal to height of image by height of object. You got magnification as 2 from here. Height of object is 5 centimeter. When you do the calculation, you'll get height of image is 10 centimeter minus 10 centimeter. So the minus indicates that it's real and inverted, and magnification is 2, which indicates that it's magnified. Yeah. Any doubt?
No, no.
So this is the last question. So I'll do it. Okay, I'll quickly do it. You have your image distance as 30 centimeter. First of all, identify the lens. 1 second. So wait. Okay, 1 second. It's the pen. Okay. So if you read the question, you will see that the height of the frame is 3 centimeter. Okay. Okay. So it's given that the image is formed on a screen. So what can you get from this? Can anyone remember? Recall. Just if an image is formed on screen, then what kind of a lens will it be? Or mirror? Any idea? Okay, so basically convex. Okay, it's a real image. Real image formed. It's, what do you say? Real images form on screen, and a real image is formed by
The
convex.
question is too small. I can't see.
Okay, I'll just read it out for you. The image of a candle flame is placed at a distance of 30 centimeter from a spherical lens formed on a screen. This small point that you have over here, it just changes the whole thing for you. Now, if you remember, I told you about sign conventions for lens. I mean, for mirrors, it's literally the same thing for lenses, except that the origin is taken as optical center instead of pole. That's the only difference. Now, the sign convention is really important for you to solve the problems, and it differs between convex and concave. So over here, you got to know that it's formed on a screen. So it is convex lens. That makes a huge difference. I can show you why. So over here, the image is formed at minus 30 centimeter. It will always be minus. U is always minus. You can just keep that in your mind. Okay, this is where the changing point comes. V is plus 60 centimeter. I wrote plus because it's a convex lens. We remember that when it's a convex lens, the object is over here, the image is formed somewhere over here. And we know that from the sign convention, we know that when the image is formed behind the mirror, I mean the lens, then it's positive. That's how we learned the sign convention. So this will be positive. But if it was a concave, then it will be negative. So that's why you need to first know which lens you're doing things with. So you have to find the focal length first. 1 by v minus 1 by u. Minus 1 minus 2 by minus 60. So we have f is equal to minus 60 by minus 3. Let me just check if it's right. It should be 20 centimeters. One second. It is, the answer is 20 centimeter, correct. It's 20 centimeters, okay? Okay, so f will become 20 centimeter plus 20, okay? Now you're asked to find the height of the flame is given. Height of the flame, you take the flame as an object. So height of the flame is plus 3 centimeter. Height of the image we have to find. No need O. So m is equal to minus v by u. First of all, we'll find magnification. Minus v means minus 60 by minus 30 is positive 2. So you got something over here. We'll get back to this, okay? We'll get back to this. So m is equal to 2. Now we also have another relation. M is equal to h dash by h. 2 is equal to h dash by h. H dash we need to find. H is given as 3. H dash is equal to positive 6 centimeter. 1 minute. Positive -2. This magnification is -2. So your height of the object will be -6 centimeter. Again, you can find the mistake. Like as you can make these small mistakes, but you can find it out as well. You can easily find it out. We are over here. We're playing this question out with a convex mirror. In a convex mirror, the image formed is inverted. We know it. So magnification can never be positive though, because it's inverted, right? So it should be negative. Second thing, height of the image should also be negative because it's formed below the principal axis. Okay, so everyone understood this? This is your solution. Same thing, you can see that you found the focal length as 20, then your magnification is -2. You're not doing it over here, but then that's how they're doing it. They're just doing it together. So your magnification will be -2, and if you multiply it with +3, you get -6. So the inverted image of the flame height will be -6 centimeter. And from the minus, you can get to know that the image is inverted, real, and so your height of the object is 3 centimeter, height of image is 6 centimeter, so it is enlarged as well. So everyone understood this? Any doubt? Anyone, Fabio, anyone doubt? Any doubt?
No.
Okay, then that's it. That's it. So from this two things, anyone has any doubt? No doubt, right? From numericals and ray diagrams. No doubt, right?
No.
Okay, fine then. Then you can leave.
No.
Okay, then thank you. That's it.
There's no test, no?
No test.